So I'm going to pass on now from filtration onto chemical treatment. And one of the first considerations is going to be money. And when you have a salesperson come onto your nursery or greenhouse offering to help you out with a water treatment system, just keep in mind a couple of things. One is that water treatment per se doesn't add value to your product. Okay? It's really just one of several risk management strategies to avoid possibilities of disease. So you therefore need to consider that in terms of investing in water treatment versus other investments that you might make. The volume's important. How much water do you really want to treat? Are you going to treat the entire nursery, or are you going to prioritize to, for example, the particularly disease-sensitive crops, or in your propagation area, your drip area, where you're having clogging issues, or plants that are particularly sensitive to disease? And that volume decision is important as well in terms of which technology you're going to select, because for the most part, you're either going to pay now or you're going to keep on paying in the future, because there are a wide selection. There's a wide selection of technologies available. Some of them have a high capital investment cost. You pay now, but a low operating cost per 1,000 gallons, whereas others, simply a matter of adding an injector in line and pumping out from a tank or from a tablet injector, and very low investment cost, but you're going to pay some for the cost per 1,000 gallons. So here's one comparison in terms of cost, where if we look at installation cost versus operation cost. Installation cost here, this is looking at a 5-acre nursery, and one dot would be less than $2,000 per to install it. 3 dots would be more than $10,000. Okay, and the operating cost, if it is 1 dot here, it would represent less than 25 cents per 1,000 gallons, and 3 dots would be more than $1 per 1,000 gallons. So if we go through the examples here, there's such a wide range of filtration costs, you're likely to be paying more than $10,000 for your filtration system. But the operating cost is low. Chlorination is very widely used because of its pretty low installation costs, and also a low operating cost, especially if we think of the 3 chlorine forms. Gas is the cheapest, followed by liquid sodium hypochlorite, followed by calcium hypochlorite. All of these are going to be less than about 15 cents per 1,000 gallons. Chlorine dioxide is a different chemistry from chlorine. It's a dissolved gas. It's generated on site. There are a couple of different technologies. You can either buy a product that you add into a single stock tank. That's just one tank option. Very easy to add into the system, but it's going to have an operating cost which is going to be over $1 per 1,000 gallons. Or you can have a multi-tank system with a dosage system, which you either purchase, which would be your 3 dots, or you lease, which would be your 1 dot, and it's going to have a lower operating cost per 1,000 gallons than a single tank system. Copper ionization is an example of an upfront cost but low operating cost. Heat is used mostly in Europe. Significant investment cost and a moderate operating cost. Activated peroxygen products, there's a range of those products available. Very low investment cost, but the operating cost varies from moderate to high compared with some of the other technologies. Hypochlorous acid, similar. There's a product called oxide available, mostly used for avoiding clogging of irrigation lines. Ozone, more of an initial investment cost, as are slow sand filtration, constructed wetlands, or ultraviolet light, but all of those have a low operating cost. Another way to compare these technologies is in terms of whether they have a residual effect and also their reaction time. So, for example, if you filter the water, it's not going to have a residual effect after the filter. It's a point treatment. And you look at these other technologies here, they have some residual. So you inject the chemical, and it's going to have some treatment effects downline and perhaps even after the water leaves the emitter. Heat is an example of a point treatment. Activated peroxygens have residual. Ozone has a short residual and also raises the ORP, oxidation reduction potential, and so in that way has some ongoing effect. And then these other treatments here are point treatments as well. The treatments vary in terms of how quickly they work. So, for example, copper ionization will have a reaction time often in terms of hours for control of certain pathogens. So it's particularly good if there is a holding tank with allowing time for the copper to react with the membranes on the microorganisms. Whereas you've got oxidizers such as chlorine, chlorine dioxide, activated peroxygens that have a rapid reaction time. So the way that you set up your system in terms of needing a holding tank for reaction time to occur is going to vary depending on the treatment technology you use. And anywhere that water is stored, you need to consider having a residual treatment in place, because even if you treat before you treat the water before it goes into that holding tank, you've got this nice environment for microbes to grow in. An example there was a grower that we worked with where we looked at the bacteria counts for their well water before it had gone through an RO system, reverse osmosis system, and afterwards, after it had been held in a tank before they used it out in the crop. And what happened was we saw that the bacteria count coming out of the well were low. I'm sure that it was even lower after it had immediately gone through the reverse osmosis, but after that water had sat in that tank, the microbial counts went up again because there was no residual treatment from the RO. Chemicals alone are not going to control all the pathogens. So you can't, again, in designing your system, can't rely just on this water treatment technology, this one chemical, to give you complete control of disease. Here's a summary of work by some plant pathologists at different institutions. They found that consistently 2 parts per million of free chlorine controlled zoospores of Pathogen Phytophthora, which are often our main targets for water treatment for pathogens. But different life stages, such as the mycelial threads, required a higher concentration. There are certain other pathogen organisms that require even a higher concentration than that 2 parts per million, and that quite often even 2.5 parts per million of free chlorine can cause phytotoxicity, and 5 parts per million is very high for many woody ornamentals. Okay? So if you're going to try to get control of fusarium with that chlorine system, it's very likely that you're going to run into phytotoxicity. And you can't, therefore, just rely on chemical water treatment as a complete answer to pathogen control. Another principle is that the more water that runs off your crop, if you're going to recirculate it, the more you're going to have to treat. And we did a trial where we looked at the water running off through propagation trays, collected that leachate, and that's the leachate that would turn up in a return tank or into a catchment basin. And here are 8 different growers, and this is the number of gallons that were leached per acre over 4 weeks. You can see it varied by a factor of 10 between grower B with lots of water and grower A with a very small amount of water. Grower B then would have to treat the equivalent of a large swimming pool each month per acre and a much higher cost than grower D. And there's also runoff not just of water, but also of nutrients. And that, in this case, was equivalent to 3 bags of 20-20-20 in terms of nitrogen being leached from one of these growers. So the more you leach, the more expensive the system's going to be. You also want to keep it simple. These technologies vary widely in terms of the complexity of the technology. For example, a chlorine tablet doser is a very simple piece of equipment, whereas something such as this ozone system here is a very sophisticated and very effective treatment system. But whether a grower is likely to have the skills themselves or the time to really maintain one system or another is going to vary. So if you're choosing a technology that you can dose with a simple injector, such as a chlorination system or copper ionization, then on-site maintenance and monitoring are very realistic. If you have a more complicated system, then you really want to have a good relationship with the provider of that system so that they can ensure that the technology is working well, because it's not just a matter of buying that piece of equipment, leaving it by itself, and expecting it to run continually. Now, it would be very nice to be able to say, okay, here's the best technology, but it all depends on what your irrigation system is and what the problems are that you're running into as to what the best technology is going to be. And all of these are going to work in some situations and not in others. So use the technology in the right way, or don't expect it to work at all. So let's run through now some different system designs. We'll start with the most simple one. You've got a well water or a municipal supply. You're just pumping from that well out into the nursery or the greenhouse. You're starting with a high-quality water source. Okay, you may need to have some filtration. It's probable that it's going to be probably particles, so something like a screen filter is going to be effective. You may need some water treatment in terms of acid injection if you have high alkalinity, or perhaps reverse osmosis or blending of other water systems with a more pure water system, water source such as rainwater if you have high EC or high salt electrical conductivity. And you may want to put a sanitizing agent in the system if you run into problems of clogging of your irrigation lines or algae on your crops. But if you're not running into those problems, you probably don't need a water treatment system in terms of a chemical at all. What chemicals would be suitable in that situation? Well, there's a number of them that are going to work. Okay? The starting point would be chlorine. Why? Because it's a low-cost system in terms of investment. It's a low-cost system per 1,000 gallons. It's very well researched. There are other technologies as well that could be very effective. Chlorine dioxide would work, although our work indicates that in terms of the mist system, it off-gases very quickly, may not be the best technology in that case for algae control, but very effective for control of biofilm. Copper, it's a slow-acting chemical. So whether it's going to be very effective for biofilm control, it may help suppress biofilm development, but it's probably not going to work quickly enough to give you very good control of biofilm. It's certainly going to be a good technology in terms of providing some residual control of algae. Activated peroxygen products such as X3, Xeritol, Sanidate provide both control of biofilm as well as algae control. Okay, some growers find that these products are not adequate for the biofilm control and move to other technologies such as chlorine dioxide. Ozone is a very fast-acting oxidizer, very active oxidizer. So certainly for biofilm control, it could be effective, unlikely to have much residual effect once that water leaves the emitter. UV is a point treatment, so would not be suitable in these cases. So treating biofilm, that's one of the problems we've talked about. First thing would be to flush out your system, always clean before you sanitize. You need to shock with a rapid-acting oxidizer such as chlorine dioxide, or an activated peroxygen product. There are label instructions for chlorine dioxide and activated peroxygens on how to do this. Typically 20 to 40 parts per million, for example, of chlorine dioxide. And if you go online, there's information there as well with chlorine. Typically an overnight treatment. So that's a high concentration. You flush the lines out. There's a lot of gunk comes out. You may have to repeat it. You're not going to want this solution to go out onto your crops. So you have to find some time and some way of flushing your system out without applying that messy residual out onto your crops, or it's going to keep on clogging up your equipment, as well as cause phytotoxicity. And then to suppress buildup, there are a number of different sanitizers that could be provided in line if an occasional shock is not adequate. So that's to treat biofilm and clogging of emitters such as we're seeing here. algae control, then there's a couple of different ways of looking at algae here. One of them is controlling the algae out in the nursery or greenhouse environment. In that case, we need a sanitizing agent that's got residual activity. So a couple of examples would be copper ionization and activated peroxygens. There's also treatment of spores that are in the irrigation water itself. And so there you want some rapid acting control. And so, for example, chlorine dioxide would control the spores in line in your irrigation lines. But how much residual effect you're going to get in the media or the environment outside is going to be a matter of testing, measuring how much active ingredient is left after it's been oxidizing any microbes that are in the irrigation water itself. So there's algae, that are spores that are in the growing media, in the environment, as well as algae spores that are in the irrigation lines. We've done a lot of testing of algae control in mist systems. This is work that Javier Lopez and my group has been doing. And one of the things is, this is with no fertilizer in the mist or fertilizer in the mist. When we put fertilized water in a mist system, we're creating a perfect environment for algae. We've got a nutrient supply, we've got warmth, we've got moisture, and we're going to grow algae for sure. If we add a sanitizer to this fertilized water here, we get varying amounts of control. Copper sulfate or copper ionization, consistently effective. Xeritol has been a very effective product here. But one of the things is, we can get control as we increase the concentration of the sanitizing agent. But by the time, if we've got a very moist environment, if we're not doing a good job of water management, we're going to get algae control. We're going to get algae growing. And if we're putting on enough sanitizing agents to control the algae, we're also going to get some phytotoxicity in the plants. So we've quite commonly seen at 2 parts per million on sensitive varieties such as Torrenia or in this case Coleus, we'll see micronutrient toxicity. With Xeritol at 1 to 1,000, then we can see in sensitive varieties some phytotoxicity as well. So you can use one of these sanitizing agents to help suppress algae, but it really comes down to water management. Now, another thing that's important, we were talking about matching the technology to the irrigation system. Our first example, we had no water-soluble fertilizer. So it would be an example of for a nursery grower who has controlled release fertilizer in their containers and they're just irrigating with clear water. Well, when we add a water-soluble fertilizer into our irrigation water, then it can potentially react with the sanitizing agent. And that's certainly true with chlorine. This is work from Dustin, where what he was doing was looking at the parts per million, or milligrams per liter, of free chlorine when that free chlorine was applied at 2.6 parts per million to a solution that either had no salts in it, it was deionized water, or it had fertilizer solutions, all of these different ones here, at 200 parts per million of nitrogen and pH 6. And what he did was Dustin measured the concentration of chlorine 2 minutes after the chlorine was mixed in with the water-soluble fertilizer. He also measured again the blue after an hour. What you can see is that without any presence of fertilizer, then the chlorine remained as free chlorine. But any ammonium in the fertilizer reacted very quickly with the chlorine to form a new compound called chloramines. Here we've got potassium nitrate, which does not have any ammonium in it, and you can see that it did not have that effect. And urea slowly reacted with chlorine. Chloramines are sanitizing chemicals. They're not as strong as free chlorine or hypochlorous acid. There isn't any research work that we're aware of on chloramines for control of plant pathogens. So that would say to us, until we know better, chlorine is probably going to be not such a good choice as a sanitizer if we're also injecting water-soluble fertilizer. We know we get some control of algae, probably some control of pathogens and biofilm, but how much we just don't know. Now, chlorine dioxide is a different chemistry to chlorine, even though they've got a similar name. And we've done some work here in our lab, and plant pathologists have done work looking at Phytophthora control with chlorine dioxide. And what we know is that the chemistry of chlorine dioxide differs from that of chlorine. It does not react in the same way with water-soluble fertilizers. It will react somewhat with iron chelates. But even in the presence of water-soluble fertilizers, chlorine dioxide, as is the case with, for example, ozone and copper ionization and activated peroxygens, will still have some control. Okay? So if we look at this situation here now, we've got clean water going through a filter system, and we've got perhaps acid injection, but we're adding a water-soluble fertilizer. Now our selection of materials probably differs. In terms of what we know at the moment, in terms of where I can safely say we've got data from plant pathologists or from testing, I would rule out chlorine as being the most effective material. It would favor chlorine dioxide or peroxygens or ozone as options. In my lab, we're going to be doing some work on this chloramine question in terms of algae control and biofilm control coming up later this year. Okay, so now let's switch to a situation of having a catchment basin or pond. And now we've got not such a clean water source. We've got high organic load, so we've got microbes growing in the pond, and we've got high sediment. And we've got potential redistribution of pathogens from the crop back through the system into other crops. This is a fairly typical kind of a setup for control water treatment at the moment. You would take pond water, we filter it, often through only one filter. We add a chemical treatment such as chlorine, and then we apply it back onto the crop. We collect our runoff water and cycle it that way. And so we have the issue here of sediment, particles, algae, and pathogens in that pond. So one of the other aspects in terms of the treatment of this type of water, which is what Ken Wagner was talking about, was having a series of treatments going on in the pond and immediately before that water gets filtered and treated. But perhaps this may be a better solution. And some growers take this approach. They increase the amount of filtration. So they're going to have a multiple-stage filtration, recognizing that they need to get down to an acceptable amount of demand before we have any chemical treatment. And our target, suggested target, is 20 parts per million of total suspended solids. They have a residual chemical treatment. They increase the contact time by that solution bit going into a holding tank. They now have to often double pump the material, the water. They may need to filter again. For example, let's say we're chlorinating in that water. That was our residual treatment. Then we may have, for example, oxidation precipitation of iron and manganese compounds from the water, which precipitate out, and we need to filter that before we apply it back to the crop. So this may be a more effective, more reliable way of ensuring that you're going to get control of that water. You're removing the demand, you're increasing the contact time, and you're increasing the likelihood of control of pathogens and algae. And there's a trade-off between the concentration of the chemical treatment, the sanitizer, and the contact time. So you may be able to get an equal amount of control with a longer contact time, a lower concentration, reduced chemical costs, and less likelihood of phytotoxicity from the active ingredient from the sanitizer. And another key aspect here is that really, to have this in an effective system, you have a potential problem from this recirculation is testing. So we really want to be testing, are there pathogens in this catchment basin here? We can send samples off to a lab to plate out Pathogen, Phytophthora, other organisms if need be. We can test the suspended solids to check whether we're getting adequate filtration. And post-treatment, we can test whether we're getting, again, we can send samples off to see, do we have actively growing pathogens, Pathogen, Phytophthora, etc., in our irrigation water before it goes onto our crop. The most challenging kind of system is where we have flood floors or sub-irrigation benches. And the situation there is that we have a very high organic load from the peat and other substrate particles that are being recirculated. We've got the possibility to distribute pathogens, and we've got rapid recirculation. So this is a pretty typical type of a system in place at the moment, where we have municipal or well water supply, goes through a screen filter. There's a fertilizer injector and usually acid injection going into a sub-irrigation tank. The water gets applied to a crop, goes through usually just single filtration, and then there's some type of a chemical treatment. It may be copper ionization, it could be chlorine or bromine or ozone. And so there's chemical treatment, and then the water gets returned into that tank. It's all happening in a very rapid cycling time because of different bays in a greenhouse operation getting sub-irrigated. So challenges that we run into, one is we clean the water with the chemical treatment, and then we're returning it back into the contaminated tank. So this recontamination is an issue. And another issue is that the filtration, when we have tested the suspended solids before and after filtration, because that water is flowing so quickly through the filter systems, very little suspended solids is being taken out. So if the solution to pollution is dilution, then I would suggest that the negation of sanitation is recontamination. And here's an example of where that kind of applies. We had one grower in Florida who was producing Syngonium liners. They had a well water, so they had good quality water, going into a tank. It was being applied to the crop, being filtered through a coarse filter and coming back into the tank. There was a recirculation loop with a UV light source, which probably wasn't very effective because of the high turbidity in that water. But any contamination that was going on to any pathogens that were coming from these plants here were being returned into the clean well water and after treatment with that UV system. And there was also no residual from the UV. So a more effective system for that grower was to, rather than recirculating that treated water back onto the crop, was to not use any recirculated water at all on these sensitive crops. So they basically, the most important thing they did add a copper ionization system into their treatment here, in their treatment loop. But the most important thing they did was to not use recirculated water on those sensitive crops. So now the water was going onto those plants, it was getting filtered, going back into the tank. There's a recirculation loop here in treatment, but that water was never going back onto those sensitive Syngonium. So avoid recirculated water on sensitive crops, and don't mix treated water with dirty water. There's some work we're doing at the moment just understanding ozone systems, and there may be some similarities as well with ozone. These are the bacteria counts which we're measuring from water that's come out of a sub-irrigation tank. It's had ozone injection, and then we're doing a count of bacteria or fungal counts in terms of colony-forming units per milliliter. And this is work that Dustin Mehta is doing. And what he's seeing is that very consistently, if we take a water sample immediately after that injector, then we have very low microbial counts, indicating very rapid and effective sanitation of the water. But if that water then goes from the injector, goes back into the sub-irrigation tank, then we see that the bacteria counts are very high inside the tank. So here we've got a circulation loop where the dirty tank water is coming up into an ozone injector. Could be a different kind of injector. The principle's the same. Getting treated, getting cleaned, and then going back into the sub-irrigation tank and getting recontaminated. And so here, in this case, we can actually see that the bacteria count in the tank increases as we have small number of tank cycles, probably because at that point we're just oxygenating the water by passing it through the ozone injector. And afterwards, eventually the ORP climbs high enough in the tank to get good kill. But if we took this water here that's already cleaned and didn't recontaminate it, we'd have a more effective system. So perhaps a more realistic approach for flood floors would be to treat with a chemical, filter, put into our sub-irrigation tank, apply to our crops, have improved filtration to reduce suspended solids going back into the tank. We then, rather than chemically treating in a loop in here, we take water, filter it, treat it with some intense treatments such as chlorine dioxide or ozone, UV. We have it in a reservoir. We have contact time, and all of the water in that reservoir is treated, and perhaps this is what happens overnight. We then filter it again, perhaps even chemically treat it again, and we start afresh the next day with clean water. So what we're trying to do is avoid treating and returning that treated water to a contaminated source.